In today's video, we're going to discuss a different coordinate system that was developed by Newton called the polar coordinate system. And it's very different from our standard Cartesian coordinates that we are used to working with so far. So this polar coordinate system, we're going to start by choosing a point that we're going to call the pole or the origin, and I'm going to call it O. And we're going to have a polar axis, which is a ray that extends from the pole, and usually we draw it horizontally to the right. Then if I have any other point P in the plane, so let me just pick this point P up here, we describe this point P with the polar coordinates r theta, where r is this distance between O and P, and theta is this angle in between my polar axis and where my point P lands. So we all agree that if P and O are the same point, then the R is going to be equal to 0. And so we agree that the point 0 theta is my point O for any value of theta. Now, we also can extend to negative values for our R, even though R is a distance, by considering a negative R being going in the opposite direction of where my theta ends. So what I mean by that, we agree that negative R theta and R theta lie on the same line through O, and the same distance, absolute value of R from O, but on opposite sides. So if this is my O, and let's say here's my point P, which is R theta, then over here, on that same exact line and the same distance, I have some other point that we're calling negative R theta. And that is exactly the same thing as the point R and theta plus pi, because I've gone another half circle around. So what I'm trying to say here is that there is more than one way to represent a single point in polar coordinates. You just keep adding a pi and you get another point that's equivalent to the point you had before. So let's do some examples so we get used to how this coordinate system works. So we're going to just start by plotting some points. So we're just going to plot the points whose polar coordinates are 1 and 5 pi over 4, 2 and 3 pi, 2 and negative 2 pi over 3, and negative 3 pi over 4. We have a lot of different points to try to graph real quick, and I'm just going to start with that point 1 and 5 pi over 4. So here's my origin, my pole. And so this point 1, 5 pi over 4 represents a point that is distance 1 from this pole, and I have an angle of 5 pi over 4. So an angle of pi would get me over here to the other side, 5 pi over 4, I have to go over to this spot here. Just remember where 5 pi over 4 is on the unit circle. And so I know that my point 1, 5 pi over 4 is on this line, and it's a distance 1 from the origin. So I'm going to say it's this point right here, where this distance is equal to 1. All right, so the point 2, 3 pi well, let me start by drawing my pole, my polar axis, and we're trying to graph the point 2, 3 pi. So the angle 3 pi, I know going all the way around once is 2 pi. Going around halfway again would get me 3 pi. So this angle 3 pi lands over here where pi was, and then I'm a distance of 2 away from the origin. So here's a distance of 2. And notice at this point 2, 3 pi, I could also write it as the point 2 pi. It would land in the exact same spot as my 2, 3 pi landed. I could also say that it's 2, negative pi. Because if I go negative pi for my angle, I'm going around clockwise, and I land still at that same angle and still have my distance 2. There's a lot of different ways to write this particular point. Okay, now let's try to graph 2, negative 2 pi over 3. So again, start by drawing your pole and your polar axis. Negative 2 pi over 3, well, the negative means that I'm going around clockwise. 2 pi over 3 means I'm going 2/3 of the way to pi. So that's somewhere around there. There's my theta. And then my distance of 2 would give me my point. If this distance here is 2. All right, last one, which is a little bit trickier. My point negative 3 pi over 4. And it's trickier because my r happens to be negative, so we have to remember what that means. But first, let me draw my pole and my polar axis. 3 pi over 4 is going to be 3/4 of the way to pi. So that's going to be at this angle here. So this is 3 pi over 4 for my angle. But now I have a distance of negative 3. So if I have a point up here, this would be a positive distance. A negative distance puts it over on the other side. So if this distance here is equal to 3, then this point down here is the point negative 3 pi over 4. All right. So now let's write down a relationship regarding these polar coordinate points. Any point represented by r theta is also represented by r theta plus 2 pi times n, so 2n pi, and negative r theta plus 2n plus 1 pi, where n is an integer. So that's just explaining how there's so many different ways to write all of these different polar coordinates. So now you might be wondering, what's the relationship between polar coordinates and our Cartesian coordinates, x, y, that we're used to? Well, here's the relationship. So the relationship between polar coordinates and Cartesian coordinates is given by x equals r cosine theta, y equals r sine theta, and we can also use r squared is x squared plus y squared, and tangent theta is equal to y over x. So we're going to use these relationships here to translate some points from polar to Cartesian and from Cartesian to polar, just so we get used to this relationship. So let's write the point 2 and pi over 3 in Cartesian coordinates. Well, I know x is supposed to be equal to r cosine of theta. So what I have is x is r cosine theta, which for this point here, my r is 2, my theta is pi over 3, so I have 2 cosine of pi over 3. Cosine of pi over 3 is 1/2, so I get that x is equal to 2 times 1/2, which is 1. And now I'm going to do the same thing with my y. Y is equal to r sine theta, so I get 2 sine of pi over 3. Now sine of pi over 3 is square root of 3 over 2. So 2 times that, I get y equals the square root of 3. So that means that my point 2 pi over 3 in polar coordinates is the same thing as the point 1 square root of 3 in Cartesian coordinates. That wasn't too bad converting between polar to Cartesian. And now we're going to go the other direction. Let's represent the point 1, -1 in polar coordinates. So I need to figure out what r is and what theta is. And I know r is equal to, well, I don't know exactly what r is equal to, but I know r squared is x squared plus y squared. So since r squared is x squared plus y squared, I get a 1 squared plus a -1 squared. So I know r squared is equal to 2. This means that r is the square root of 2. And then to figure out my theta, I'm going to need to use that other relationship involving tangent. So my tangent of theta is equal to y over x. So on this particular point that I have, I get tangent of theta is equal to -1. This means theta is the inverse tangent of -1. And so I get that theta is -pi over 4, and that's the same thing as 7 pi over 4. Now I'm going to point out there are other values for inverse tangent that gets you inverse tangent of -1. You can get other angles other than these two. I chose this particular theta because my original point that they gave me in Cartesian coordinates was 1, -1. So it's somewhere down here in the 4th quadrant. So the angle that I'm looking for is this angle down here, which would be my -π/4 if I go clockwise. Or if I go counterclockwise, this is the 7π/4. You also have tangent inverse of -1. You get a value over here as well, but that one doesn't match up with the point that I had originally, so I didn't choose that particular value for theta. So I have polar coordinates √2 and 7π/4 representing that same point that we were given in Cartesian coordinates. All right, so now we get to the really cool stuff, talking about polar curves. So the graph of a polar equation, r equals a function of theta, consists of all points that have at least one polar representation that satisfies the equation. So the graph of r equals some f of theta consists of all points that have at least one polar representation that satisfies the equation. So we're going to do a few examples where we just graph some polar curves. It's going to be a little interesting trying to do that because your brains are used to graphing in Cartesian coordinates, and now we have to convert our brains to thinking in this new coordinate system. But the graphs of polar curves are usually really cool looking, so it should be a lot of fun. We'll start with a very simple one. So what curve is represented by the polar equation r equals 2? So let's think about what that means. They're talking about the distance from the pole is 2. But notice that I don't have any thetas that I'm dealing with here, so theta can be anything. Our angle is anything. So if I think of, here is my origin or my pole, here's my polar axis, and I need to graph all of the possible points that have a distance from this O as 2. What's that going to look like? It's going to look like a circle. A circle that has a radius of 2, centered right at my pole. All right, so that one wasn't too bad. We need to do something more interesting though. So let's sketch r equals 2 cosine of theta, and we'll find a Cartesian equation for this curve. All right, so I have r equals 2 cosine theta. what I would suggest is if you don't know exactly what that's going to look like, go ahead and just start picking values of theta and find some points on this curve. So let me write down just a brief little table of points. I have my theta and I have r is 2 cosine of theta. And of course, you should pick values for theta that are pretty easy to work with. For example, theta equals 0 would get me r equals 2. If I do theta is pi over 6, I'm going to get r is equal to a square root of 3. If I choose theta as pi over 4, well then cosine of theta is square root of 2 over 2, so my r is going to be a square root of 2, and so on. And you would just keep plotting different points. So here's my point 2, 0. And if I plot all of these other points going around, you end up with a circle that ends up hitting at my pole. Over here is the point 0 and pi over 2. Because my angle here at pi over 2 is straight up and down, and I'm at a distance of 0. If I get to my angle of pi, I'm going to get negative 2 for my distance, so I end up back over at this point over here. So that's yet another circle, but it's a circle that's not centered at my pole anymore. To find the Cartesian equation, remember that we know that x is r cosine of theta. So I know for a fact that x over r is equal to cosine of theta. That means that when I have my equation, r equals 2 cosine theta. That's the same thing as saying r equals 2 times x over r. And so I get r squared is equal to 2x. Now, do we know what r squared is equal to? Yeah, r squared is x squared plus y squared. That was another one of our relations. So this gets me x squared plus y squared equals 2x, which is a Cartesian version of this curve. So this technically is a correct answer for our Cartesian equation of that curve. But if instead I decided to rearrange this a little bit, move the 2x over and complete the square, I will get x minus 1 squared plus y squared equals 1. And that is a circle with radius 1 that has center 1, 0, which is exactly what we drew earlier. All right, let's do some more sketching. So, let's sketch the curve r equals 1 plus sine of theta. And the way I sketched the last problem, we came up with a table of points and plotted some points to connect the curve. I'm going to show you a different way to plot our polar graphs now as well. You could, if you wanted to, first graph this as if it were a Cartesian equation, and then use that information to translate it to the polar graph. So what would this look like if I graphed it as a Cartesian equation? All right, so if my angle is going to be 0, we know sine of 0 is 0. So I'm actually going to start up here at 1. Sine of pi over 2 is 1, so I get 1 plus 1 is 2. And you know how the rest of this graph ends up looking. You guys have graphed sine curves many, many times. So I end up getting that for my Cartesian graph of 1 plus sine theta. But that is not my polar graph. What we should notice, though, is when my theta increases from 0 to pi over 2, I'm going to be my distance from the origin is increasing from 1 to 2. So here my distance, r, changes from 1 to 2. And then in between pi over 2 and pi, my distance from the origin is going to decrease, and it's decreasing from 2 to 1. Between pi and 3 pi over 2, my distance is decreasing from 1 to 0. And then between 3 pi over 2 and 2 pi, my distance increases again from 0 to 1. So if I put that information all together, I get what the graph of r equals 1 plus sine theta looks like as a polar curve. So here's my O, and again, I'm starting at a distance of 1. And when I go from angle of 0 to pi over 2, my distance increases from 1 to 2. So I get that part of the curve up there. And now as I go between pi over 2 and pi, which is over here, my distance decreases from 2 to a distance of 1. Between my pi and 3 pi over 2, my distance decreases from 1 to 0. Distance of 0 means it's right at my point O. And then between 3 pi over 2 and 2 pi, my distance increases from 0 back up to 1. And I'm usually a pretty terrible grapher. This is pretty good for me. You actually see what this is supposed to look like. This sort of a graph is called a cardioid because it kind of looks like a heart. So when you have a graph that looks sort of like a heart, we call that a cardioid. Let's do another polar graph. Let's sketch r equals cosine of 2 theta. And I'm going to do a similar procedure to how we did the last problem. So first, the Cartesian version. I have, here's pi over 4, pi over 2, 3 pi over 4, pi, and it just keeps going on from there. Here's 1, here's -1. When my angle is 0, I'm starting up here at 1. At pi over 4, I get cosine of pi over 2, which is 0. At pi over 2, I get cosine of pi, which is -1. Then I'm going to get back to 0, back up here at 1. And if I continue this all the way through 2 pi, it would keep repeating and look exactly the same from there. So what's going on here is between an angle of 0 and an angle of pi over 4, my distance is going to be decreasing from 1 to 0. And then between pi over 4 and pi over 2, it's going to increase from 0 to 1. Then we again decrease from 1 to 0, increase from 0 to 1, and it continues like that all the way through 2 pi. So what does this look like? Let me give myself a little bit of guidance here. Put angles for the pi's over 4. All right, so what I had is, again, between an angle of 0 and an angle of pi over 4, I was starting at a distance 1 and decreasing to a distance of 0. So I get that little piece of a curve here. Then between my pi over 4 and my pi over 2, I increase to a distance of 1 again. But it was a negative 1 because I was on the other side. So a distance of 1, but on the other side is down here at negative 1. And then I continue. I decrease back to a distance of 0. And then I'm going to increase to a distance of 1. Decrease to a distance of 0. Increase to a distance of 1. Decrease to 0. Increase to 1. And I get this nice curve. All of those petals should be the same size. It's actually not too bad. But this is called a 4-leaved rose. I guess because it looks kind of like a flower, so they gave it that name. It's 4-leaved because I have 4 different petals on this particular curve. All right, so all we've done with polar coordinates so far is a lot of sketching, converting between polar and Cartesian. Now we have to actually do calculus with these things. So the first thing we're going to do is learn how to get a tangent line to a polar curve. So to find a tangent line to a polar curve, r equals f of theta, we're going to regard theta as a parameter. And write the parametric equations. X equals r cosine of theta, or f of theta cosine of theta. And y equals r sine of theta, which is f of theta sine theta. So in the last video, we knew that the slope of the tangent line to parametric curves is given by r dy dt over dx dt. Or in this particular case, since I'm using theta instead of t, it's going to be a dy d theta over dx d theta. So our dy dx is dy d theta over dx d theta. And to get those values, you're going to have to use a product rule. And we're going to get that dy dx is equal to my dr d theta sine theta plus r cosine theta divided by my dr d theta cosine theta minus r sine theta. And again, that's just found using our product rule for derivatives. So here's the formula for how you find the slope of a tangent line. You can either go ahead and memorize this for polar curves, or you can just remember how to do it for parametric curves and derive this using the product rule. Either way works. So let's do an example where we find the slope of a tangent line to a polar curve. And we're going to use our cardioid 1 plus sine theta. We're going to find the slope of the tangent line. When my theta is pi over 3. All right, so I need to use that formula that we just found for how to find our dy dx, which is the slope of the tangent line. So my x is equal to r cosine of theta. My r is 1 plus sine theta. So x is 1 plus sine theta times cosine of theta, which is equal to cosine of theta plus cosine of theta sine of theta. And my y is equal to r sine theta. So again, my r was equal to 1 plus sine theta. So I get my y is equal to sine theta plus sine squared of theta. So now if I'm going to find my dy dx, I need to use these two values for my x and my y. Let me just rewrite this so I have what I need. X is cosine theta plus cosine theta sine theta. Y is sine theta plus sine squared of theta. And so then I just use what my formula is for dy dx. My dy dx, remember, is equal to dr d theta times sine theta plus r cosine of theta over dr d theta cosine theta minus r sine theta. So I have a couple different options. I can either use this version of the formula where I need to find dr d theta and just plug in all of this info, or I can remember that dy dx is my dy d theta over dx d theta, and take the derivatives of my x and y with respect to theta and fill that in to be my slope of the tangent line. So since I already took the time to figure out my x and y, I'm going to do it that way. My dy d theta is equal to derivative of sine is cosine, and the derivative of sine squared is 2 sine theta cosine of theta using a chain rule. So that's my dy d theta. And in the denominator, I get my dx d theta. Derivative of cosine is negative sine. And then to do the derivative of cosine times sine, I would have to do a product rule. I get cosine times the derivative of sine. So I get cosine squared. And then plus my sine times the derivative of cosine, which is negative sine. So I get a negative sine theta plus cosine squared theta minus sine squared theta. And now at my pi over 3, I would just have to plug in pi over 3 for all of these. Cosine of pi over 3 is 1/2. Sine of pi over 3 is square root of 3 over 2. And then for my denominator, negative sine of pi over 3 is a negative square root 3 over 2. And then here I get a 1/2 squared and a minus square root of 3 over 2 squared. And if you simplify this all the way out, you'll get a -1 for this slope of the tangent line. Now, I did this particular slope of the tangent line by first writing out what x and y were and doing the derivative with respect to theta. We could have done it just using the formula that we used earlier. It was dy dx is equal to my dr d theta times sine theta plus r cosine theta over dr d theta cosine theta minus r sine theta, and you would get the exact same result. So that is how you find the slope of a tangent line to a polar curve. And we can do all sorts of other calculus with our polar curves. Other things that we know how to do with other curves that are not polar curves. We know how to find area between curves. We know how to find the arc length of curves. We can do all of that with polar curves as well. So let's start with the area whose boundary is a polar equation. Oops, I don't need to use green. The green probably won't show up as well. So let's use, here's a black marker. The area of a region whose boundary is a polar curve, r equals f of theta, and also bounded by the rays theta equals a to theta equals b, we get this formula for the area. Area is equal to an integral from a to b of 1/2 r squared d theta. And for those of you that are current students in my class, I will be posting the reason why this formula comes about in case you're interested in seeing where it comes from. So you can check on our course site to see where this formula comes from. We are going to do an example using this formula to find the area enclosed by one loop of that 4-leaved rose that we worked with earlier. So find the area enclosed by one loop of the 4-leaved rose r equals cosine of 2 theta. So that r equals cosine of 2 theta, that's that same curve that we graphed earlier. Our 4-leaved rose. So if you remember that graph from earlier, one of these petals, one of the loops of our rose, was right there. that is between a negative pi over 4 and a positive pi over 4 for my angle, because I'm starting at this angle down here and finishing at that angle up there. So those are the angles I'm going to use on my integral. So one of my loops goes from negative pi over 4 to positive pi over 4. And my formula was 1/2 r squared. So I get 1/2 cosine squared of 2 theta d theta. And then I just have to do this integral, and I'll get the area enclosed by one of the loops. So in order to integrate this, I need to take care of this cosine squared by using a trig identity. But before I do that, I'm also going to use the fact that this petal was symmetric and rewrite this. Instead of being from negative pi over 4 to positive pi over 4, I'm going to rewrite it as 2 times the integral from 0 to pi over 4, just to make my life a little bit easier. So now that I have it as 2 times this integral of 1/2 cosine squared of 2 theta d theta, that 2 and the 1/2 will cancel each other out. So I just have an integral from 0 to pi over 4 of my cosine squared of 2 theta d theta. Now, remembering our trig identities from earlier in the semester, I get to rewrite this integral 0 to pi over 4 of 1/2 1 plus cosine of 4 theta d theta, and now I'm able to integrate this. So we're going to pull the 1/2 out. Antiderivative of 1 would be theta. Antiderivative of cosine 4 theta is a 1/4 sine of 4 theta. And then I'm going to plug in my 0 and my pi over 4 and have some subtraction. So when I plug in the pi over 4, I get a pi over 4 plus a 1/4 sine of 4 times pi over 4. So that's sine of pi. And then minus my 1/2 times my 0 plus 1/4 sine of 0. And now we just get to simplify this as much as we can. So sine of pi is 0, and sine of 0 is 0. So most of this disappears. All that I have left is a 1/2 times a pi over 4. So I get pi over 8 for the area enclosed by one of these leaves. Let's see, what do we have left to cover? I still have to find an area between two curves, and then we're going to do an arc length, and that should finish up this video. So let's do a problem where we have to find the area between two curves. It's very similar to the stuff we did earlier in the semester. It's just now we have polar curves instead of non-polar curves, but it's still done the exact same way. So find the area of the region inside the circle r equals 3 sine of theta, and outside the cardioid r equals 1 plus sine theta, which is the same cardioid we graphed earlier. So if I were to graph what this looks like, my cardioid looked something like that, and then my circle ends up being similar to that. So the area that we're talking about, it says inside the circle and outside the cardioid. So we're talking about this area up here. So I'm going to need to integrate from whatever angle this is, where the two curves intersect each other, to whatever angle this is, where the two curves intersect each other. So the first thing we should do is figure out those points of intersection so that we can set up our integral. To find the points of intersection, set the two equations equal to each other. And then solve it for theta. So I'm going to have 2 sine theta equals 1, which means sine of theta is 1/2. And then I do an inverse sine to get theta is equal to pi over 6 or 5 pi over 6. So this first angle over here is pi over 6, and over here is 5 pi over 6. That matches what's going on in my graph, so it makes sense. So to find this shaded area, we're going to integrate between those two values. And the integrand inside of my integral is going to be the outside squared minus the inside squared, both of them multiplied by 1/2. So my area is equal to an integral from pi over 6 to 5 pi over 6. I have my 1/2, and it's the outer one squared. So 3 sine of theta squared minus the inner guy squared d theta. So now I'm just going to multiply everything out and pull my 1/2 to the outside. So I'm going to pull the 1/2 out. If you distribute everything and combine all your like terms, you're going to have an 8 sine squared theta minus 2 sine theta minus 1 d theta. And most of this is not going to be an issue, but this 8 sine squared theta, we need to use a trig identity before we can integrate that. You're going to need the trig identity that says that a sine squared of x is equal to 1/2 1 minus cosine of 2x. So when I rewrite this, I still have my 1/2. My 8 sine squared, when I use my trig identity, half of 8 is equal to 4, so I get 4 times 1 minus cosine of 2 theta. And then I still have my minus 2 sine theta and a minus 1 d theta. And now I'm ready to integrate this after I distribute this 4. If I distribute my 4, I get a 4 minus 4 cosine 2 theta, and that 4 minus the 1 gets me a 3. So distributing that 4 and combining my like terms before I integrate, I'm going to get my 1/2 integral from pi over 6 to 5 pi over 6. I have a 3 minus 4 cosine of 2 theta and a minus 2 sine of theta d theta. And now I'm ready to integrate this. So we find our antiderivative. I get a 1/2, 3 theta minus 2 sine of 2 theta, and then a plus 2 cosine of theta. And I'm plugging in my bounds of integration. When I plug in the 5 pi over 6 and then plug in the pi over 6 with subtraction in between, we will get our 1/2 times 5 pi over 2 plus square root 3 minus square root 3 minus pi over 2 plus square root 3 minus square root 3. And I combine all my like terms together, I'm going to get a 1/2 times a 4 pi over 2. That's 1/2 times 2 pi, which is just pi. So the area in between those two curves was equal to pi. All right, so now we've had some practice finding the area enclosed by a polar curve and the area between two different polar curves. Now let's practice doing some arc length of a polar curve. So let's get the formula for the arc length of a polar curve and do an example of that. The arc length of a polar curve, r equals f of theta with theta between a and b, is given by L equals the integral from a to b of a square root of r squared plus dr d theta squared with respect to theta. So if you're one of my current students, again, I'm going to post some notes showing where this formula comes from. It's not too surprising. It comes from the arc length formula that we used earlier, and for our parametric equations that we came up with last time. It's just thinking of our theta as a parameter and then translating it so that we can use it just for our polar curves without converting to parametric equations each time. But I will post those notes on our course page. But on this video, we're just going to learn how to use this formula. So we are going to find the length of our cardioid, r equals 1 plus sine of theta. Just as a quick reminder, what the graph looked like was something similar to that. So we have some symmetry going on. So right now, my theta goes between 0 and 2 pi. It goes all the way around. So I know that this arc length, using that formula, is equal to the integral from 0 to 2 pi of the square root of my r squared plus dr d theta squared. Well, dr d theta is the derivative of my r with respect to theta, so that's just a cosine of theta squared. So I have that, and let's just simplify this down as much as we possibly can. If I distribute everything underneath the square root, I'm going to get a 1 plus 2 sine of theta plus a sine squared of theta. And then I still have this cosine squared of theta, and we're integrating with respect to theta. So we know that sine squared plus cosine squared is equal to 1. So I'm going to rewrite this sine squared and cosine squared as a 1, combine it with my other 1. So when I do that, I get my arc length is equal to the integral from 0 to 2 pi, a square root of 2 plus 2 sine of theta d theta. And so since my cardioid was symmetric, I'm just going to consider the right half and multiply by 2. That's something we do a lot when dealing with the polar equations, is using the symmetry to make things easier. So by symmetry, I get that my arc length is equal to 2 times the negative pi over 2 to pi over 2, so the right half of the cardioid. So I still have to figure out how to do this integration. And to do that, I'm going to multiply in just a very interesting way. So I'm going to have 2 times my integral from negative pi over 2 to positive pi over 2. I have my square root of 2 plus 2 sine of theta, and I'm going to multiply by 1 in an interesting way. So I'm multiplying by the square root of 2 minus 2 sine of theta over square root of 2 minus 2 sine of theta. The reason I'm doing that is just to make it so I can simplify and actually do this integral. So when I distribute underneath the square root in the numerator, I have 2 times my integral from negative pi over 2 to positive pi over 2, and I have a square root of a 4 minus 4 sine squared of theta, and in my denominator, I still have a square root of 2 minus 2 sine of theta. So then in the numerator, I can factor out a 4 and take the square root of that 4. So I get 2 times the integral negative pi over 2 to pi over 2. My square root of 4 is 2. And I still have a square root of 1 minus sine squared theta. And a square root of 2 minus 2 sine theta d theta. All right, so now look in the numerator. I have a square root of 1 minus sine squared of theta. Well, sine squared plus cosine squared is 1, so I know underneath this square root, I actually have a cosine squared of theta. Square root of a cosine squared is just cosine. So I did all of this algebra to rewrite my arc length as 2 times the integral from negative pi over 2 to positive pi over 2, 2 cosine of theta over square root of 2 minus 2 sine theta d theta. And now I can do this using substitution. So if I do substitution with u equals my 2 minus 2 sine theta, I'll be able to complete this arc length problem. So again, let u equal 2 minus 2 sine of theta. That means that my du is going to be equal to a negative 2 cosine of theta d theta. And I'm going to change my bounds of integration. When my theta is negative pi over 2, that means my u is equal to 2 minus 2 sine of negative pi over 2, and that simplifies to 4. And when my theta is positive pi over 2, I'm going to get u is equal to 0. And you just get that u by plugging your theta into your u. So rewriting my integral with this substitution, we get that my arc length is equal to negative 2 an integral from 4 to 0 of u to the negative 1/2 power du. And now I'm ready to integrate. I'm going to add 1 to the exponent, divide by the new exponent. So I get negative 4 u to the 1/2, plug in my 0, plug in my 4. You plug in 0, you're going to get 0. And then you plug in the 4 and subtract. So I get 4 times a 4 to the 1/2 power. 4 to the 1/2 is 2. And so I get 8. And so the arc length of that cardioid was equal to 8. Isn't it great when you have a problem that takes that long and you get just a nice whole number as the answer? I think that's always very amusing. I don't know if you guys agree with me, but I find it very amusing when we do all of that work and get a nice whole number as an answer. So this video has a lot of information in it, all about polar coordinates, how to find the slope of a tangent line to a polar curve, how to find the arc length of a polar curve, area between polar curves. There's a lot of information in this video. Feel free to ask questions if you have them. You can drop them down below, or if you're in my class, you can email me or come to my office hours. And that's all I have for you today.